Hello, friends. Welcome to the personal tutor page. Gradually, we are drawing down the curtain on our series on dimensional analysis. For today's lesson, the specific objective is to look at the last aspect of the applications of dimensional analysis. During our previous lessons, we did look at the first two applications, where we said for the first, dimensional analysis could be used to determine the validity and correctness of an equation, as well as forming relationship between physical quantity. For today, the third and the last aspect is to look at ways by which units can be determined for physical quantities. Friends, in order to achieve the task of determining the unit of physical quantities using dimensional analysis, we need to follow a step-by-step procedure. And so, I will outline these simple steps that can help us achieve our objective for the day. The first of the steps is ensure that the quantity whose unit is to be determined is made the subject of the relation. Secondly, you then write the dependent quantities in their respective dimensions. And lastly, you solve for the outcome algebraically in order to arrive at the unit of the physical quantity to be determined. Now, let's look at these three steps in a detailed manner. The first step said, ensure that the quantity whose unit is to be determined is the subject of the relation. By this, it means simply that if you take a question like this example, which says, find the units of acceleration A in the relation F equals ma. If you look at the equation given, F is the subject of the relation, whereas m and a are the dependent quantities. But we have to find the unit of the acceleration A. So in light of this step, you then have to make A the subject of the relation, because that is the unit you are looking for. So you do so by simply dividing both sides by m, and you arrive at A being equal to force over the mass. So that is the first task. Make sure that the quantity whose unit we are trying to find is made the subject. So that's what we have done. The second step said, you then write the dependent quantities in their respective dimensions. By that, it means because we are looking for the unit of acceleration A, and that has the formula force over mass, we then convert the dependent quantities, now force and mass, into their dimension. That of the force is mLT exponent minus 2, and that of the mass is a capital M. So that is a brief description of the second step. The final step is then to solve for the outcome in order to arrive at the unit to be determined. That means that from the dimension written, you cancel out possible ones, common ones that can be cancelled. Looking at this formula here, the m can easily cancel the m, and you are left with LT exponent minus 2. So this is the outcome. From here, we are supposed to rather write units, not dimensional equation. Out of the dimensional equation, we deduce the unit. L is length and it has the unit meter. T is time and has the unit seconds. Then exponent -2. Therefore, from here, you can say that the unit of acceleration A is meter per second square. Friends, this is a simple, straightforward means by which you can achieve the task for the day. And I trust you have understood this very well. Let's then, based on this understanding, and take some illustrative examples. Great. And as we continue to take some illustrative examples, I will want you to note this. For your level as senior high school student, all your equations will have mass, length, and time. Just these 3 out of 7 physical quantities. And note that the dimensional symbol for mass is a capital M. When you are supposed to convert this to 8 units, it is kg. That is kilogram. Whenever you meet length with dimensional symbol L, 8 units is M, meter. And lastly, time. That is a T, a capital T in a square bracket. 8 unit is seconds. So you note this very well, how these dimensional symbols are converted to their unit. Let's start from example number 1. The period T of revolution of a satellite orbiting a planet of mass M is related to the radius r of the orbit by the equation t square equals 4 pi square r cubed all over gm. Using dimensional analysis, deduce the base unit of g. Okay, so that is the equation. We are supposed to find the base unit of g. And the equation is t square equals 4 pi square r cubed all over gm. If you look at this, it is t which is the subject of the relation. But we are supposed rather to find the unit of g. So per the first step, we ought to make g the subject of the relation. The simple reason that it is g whose unit we have to determine. Okay. And so, if you look at this critically, if you want to make g the subject, first let's cross multiply. That will be t square multiplying gm equals 4 pi square r cubed. In order to let g stand alone, you have to divide both sides by t square and m. So g will be alone. So t square m on the left hand side. You repeat same for the right hand side. When the common terms are cancelled, on the left hand side you will have g to be equal to 4 pi square r cubed over t square m. So g has been made the subject. That's the first thing. The second thing is you need to write the dependent quantities, and I mean 4 pi square r cubed over t square m. These are the dependent quantities in their dimensional form. And that is achieved by converting those which have dimensions. So the first is G equals 4. 4 is a number and it is dimensionless, so ignored. Pi square. Pi is also a dimensionless constant and hence ignored. R cube. This R is called radius and its dimensional symbol is L. So that will be L cube over T square. The T is said to be period. Period simply means time. And so the dimensional symbol is also a T and it is squared times the M. This M is the mass and that is also a capital M. So basically, this is how the gene has been converted to its dimensional form. We then have to work on this algebraically and solve where possible. Okay, so J would be equal to this. If it is expanded, that will amount to L to the power 3. The power will then be part of the dimension. All of this divided by the T will also be T square. Then times M will become T square M. Still on the G, let's maintain the numerator. So still be L to the power 3. Then the division sign is changed to multiplication. That is, I'm trying to bring these ones up. When they come up, they are negated. And so T, the power 2, will now become negative 2. M was originally to the power positive 1. It will now become negative 1. So J equals, let's then multiply. Look at it. L is only 1, so that will be L to the power 3. Then T to the power minus 2. Then M to the power negative 1. So this is how J has been solved dimensionally. We need then convert this to the unit form. But don't forget, I told you from the beginning that the unit of mass with dimensional symbol M is kilogram. Length with dimensional symbol of L is meter. And time with dimensional symbol of T to be seconds, S. And so if you look at it critically, the unit of G can simply be achieved when these are converted to their various uniform. For that of the length, we will have meter to the power 3. T is seconds to the power minus 2. Then M for mass is kilogram to the power negative 1. So this then becomes the unit of G, read as meter cube per second square kilogram. So this is the unit of G. Thank you very much for your audience. Let's pick question number 2, which reads, the velocity v of sound in a gas of density rho is given as v equals square root of p over rho. Determine the unit of p. Great. So from this, you can simply write this as the equation. Okay. But we are supposed to determine the unit of P. However, it is V which is the subject here. And so we need to make P the subject. And that can be achieved from here by first eliminating the square root. And that is done by simply taking the square of both sides. And so that will be V square equals the square root of P over rho, also squared. It is said that this square will cancel the square root, and you're left with V square equals P over rho, the density. From here, you could simply cross multiply, and P, when cross multiply, will be P is equal to V square rho. So this is the subject of P, or the expression for P. From here, the only thing is, let's then write the dependent quantities to their dimensional form. Okay, so P still remains as P, but we are looking for the unit of P. But V, which is the velocity, has its dimension as L t minus 1. And don't forget, it is squared. So squared follows. Then that of the density is the mass density. So that will be m L exponent minus 3. It carries no other power. So this is it. Let's then solve for the value of P in the dimensional form. Okay. But first, let's expand this. This 2, or this square here, goes for the L as well as the T. And so when expanded, you will have L square. But this will be T negative 2. The other one remains as M L exponent minus 3. Expanding, there is L, and there is another L here. So you write one of them. Because you are multiplying, the exponents are added. That will be 2 plus minus 3. And 2 plus minus 3 is a negative 1. Let's pick the T. It has got no other counterpart, and so written as negative T. Let's pick the M. It is alone. This is how it is. We could then reorganize and say that the dimension of P is M L negative 1 T negative 2. Okay. Out of what we have written so far, we can then determine the unit of the P. So P is equal to, we need simply convert these dimensional symbols to units. The first is M, mass, and it has the unit kilogram. Second, length, it has the unit meter to the power negative 1. And this is T, time, has the unit seconds, also to the power negative 2. And so the unit of the P is kilogram per meter second square. So this is how it is. Or some will say kilogram per meter per second square. This is how to determine the unit of P. Let's move to the third example. It reads, the period T of a simple pendulum of length L is expressed by the equation T equals 2 pi square root of L over G. Find the unit of the quantity G. Okay, so that is the equation. T equals 2 pi and L on G, all under square root. Great. Here it is G, which is the subject, but we are looking for G. And so let's make G the subject of the relation before we can talk about its unit. And G is under a square root, and so you will have to square both sides. But be mindful here, the T will carry a square equals these two will also carry a square. This pi will also carry a square. Before whatever is under the square root also carries its own square. So be mindful of this expansion. And that will amount to t square equals 2 square is 4. Pi square is still pi square. Here, the square cancels the square root and you have L over G. From here, we could say t square is equal to 4 pi square L all on G. We then have to cross multiply, and that will be G t square equals 4 pi square L. Okay. Our task is to look for G, and so we divide both sides by t square. You eliminate t square, so G can stand alone as G equals 4 pi square L all over t square. Okay. Now G has been made the subject. So in converting them to their dimension, G is written as 4 is a dimensionless constant as well as pi square. So you have L as the only dimension there for the numerator, divided by, for the denominator, you also have t square. Okay, solving this will be L times, this then comes up linearly, and it will be t to the power minus 2. When brought together, you have G to be equal to L t exponent minus 2. This then becomes the dimensional equation for G. And out of it, you could determine the unit straightforward. So the unit of G then becomes length has the unit meter. T time has the unit seconds to the power minus 2. Therefore, the unit of G is meter per second square. And that is incredibly good because G is acceleration due to gravity. Let's take our last example. Example number 4. The potential energy U stored in a stretched wire is given by U equals half C sigma square V, where C is a constant, sigma is a strain, and V is volume of the wire. Determine the SI base unit of C. Okay, let's code the equation. That is U equals half C then sigma square V. Okay. U is then the subject of the relation, but we are supposed to rather find the unit of C. Therefore, let's make C the subject of this relation. So first and foremost, you multiply both sides by 2 so that these 2 can be eliminated. So that will be 2U equals, we multiply here by 2, the 2 cancel. So C sigma square V. Still on the C, you divide both sides by sigma square V so that the C can stand alone. So sigma squared and V, sigma squared and V. When the common terms cancel out, you will have C to be equal to 2U over sigma square V. This is now the relation. From here, we can easily convert them to their dimension. And doing so, you then write C equals, the 2 is a number and is a dimensionless quantity. The U is energy or potential energy, whose dimensional equation is mL square C minus 2. That is it for the numerator. For the denominator, sigma. The sigma here was said to be called the strain. And friends, maybe this is the first time you are hearing this. Strain has no dimension. It is 1. So it has not got any dimension because strain is extension over our original length. And that cancels out. So strain also has got no dimension. The next is volume, V. For the volume, it is L to the power 3. Okay, so let's add it straightforward. So L cubed in a square bracket. From this context, the numerator is still maintained as M L2 T minus 2. This then comes out to become L exponent negative 3. It is negated when it travels upward to be linear. Let's expand this. We pick the M, it has got no other M, so it still remains as M. If we pick the L, there is L to the power 2 and L to the power negative 3. So once they are multiplying, the exponents are added, and 2 minus 3 is a negative 1. Then the T follows as T negative 2. This then becomes the dimensional equation of the C, whose unit we want to find. It then becomes very easy to find the unit. So the unit of C is equal to, for this as mass, it has the unit kilogram. Length, meter, the power negative 1. Then T, seconds, the power negative 2. So this is the unit of C, kilogram per meter per second square. Thank you very much for how far we have journeyed on this lesson. This happened to be the last work on dimensional analysis. But kudos, you've done very well for following up to this far. Stay blessed.